Okay, so for the course, basically you are going to learn how to derive OLS estimators for linear regression coefficients and their statistical properties. And to do that, you need to know some fundamental things about linear algebra and statistics and so on. So the purpose of the math camp for the econometrics is to get you familiar with those parts. So I want you to read the lecture note that I have sent. Here's the goal, and this is going to be the OLS regression model, and you are going to derive the OLS estimators using this minimization problem. So you are going to learn how to minimize some things, especially the quadratic things, and you're going to learn how the minimization solution of the minimization is related with the so-called projection. Okay, and here are some references that you may want to take a look at. They are very helpful for the not only for the econometrics but for the graduate life here in Korea University. So take a look at them. Okay. I think you're familiar with the notion of functions. So we use this notation function f x to y, where x is a set, a domain set, and y is a member of a range set. We can also use this notation, y equals to f of x. When the input elements are two bivariate function, in this case, we use this notation. Okay. For the notational simplicity, I'm going to use r to denote the real number, and r squared is when this this mathematical entity is an ordered pair. Every element in this ordered pair is in the real number line. Same way, if you have this notation x, y, z in r cubed, it means that this is a real number, this is another real number, this is another real number. Okay, I'm going to use this notation to denote a line segment. 0,1 squared is a pair of numbers that whose elements lie in the line segment. So this set here is, if you visualize this set, is the points in this rectangular. Here's 0, the origin 1, 1. Okay. R squared plus means the first orthant of a two-dimensional Euclidean space, though, and the origin is included. R squared plus plus is the first orthant of a two-dimensional Euclidean space, the origin excluded. You probably won't encounter this thing. The CC is a set of the space of complex numbers. and we are going to define or set every time we are going to use. Okay, and you know how to do the summation, so I want you to take some time doing these exercise questions. And mathematics is not just solving some equations. It's basically it's more about the logics, and you have to be very familiar with mathematical logics. In mathematical logics, a proposition is a statement that you can determine whether it is true or false. In mathematical logic, every statement is symbolized. We use Q, P, like this, P, Q. We are going to use the following notations. This part is the negation, so not, and we read this not P or negation of P, and this triangular shape is on end, so it's P and Q. This upside down triangular shape is OR, so this is P or Q. And operation is called logical conjunction, or operation is logical disjunction. We have this implication operation, so P implies Q. We read this statement, this notation, if P then Q, or Q if P. Okay. And later you are going to see the truth table. So for this statement implication, for this implication to be true, you have to either both P and Q true, or Q force P force to Q true, and P force Q force. So the only case that if P then Q statement is false is P is true and Q is false. Okay. And there are 5 examples here from A to E that you can work on the mathematical logic. Okay. And there's this biconditional connectivity. P, if P and Q, if P then Q, and if Q then P. So it's called the if and only if relation, and this reads P if and only if Q. And as you can see here, this if and only if relation is true. The truth value of this if and only if relation is true only when both P and Q are true or both P and Q are false. You sometimes will be asked to prove some mathematical statements, and there are 3 methods of proof. First, proof by contrapositive. means that to prove this statement P implies Q, or if P then Q, what you need is the negation of Q implies negation of P. It's called the if you take this method, this proof method, then it's called the proof by contrapositive. This statement is contrapositive of this statement. Okay. And mathematical syllogism is to prove P implies Q, you have to prove P implies R, and then R implies Q. It's called, this way of proving is mathematical syllogism. And you can also use a proof by contradiction. Proof by contradiction is to prove P, you assume P is false, and you show that assumption that P is false leads to a conclusion that cannot be true, so it's to a false. Okay. A tautology is a statement that is always true. The two statements P and Q are logically equivalent. We write this way if their truth values are always the same. Okay, so here a statement P implies Q is equivalent, logically equivalent to not P or Q. Okay, use this truth table to show that this statement has always the same truth value as this statement does. Okay. To show this is a tautology, what you need to show is that the truth value for this statement is always truth. Let's say this is your P statement. A is greater than B. And this is your Q statement. Integral x dx is log of x plus c. And R statement is a frog can fly. A new statement S is P, if P then Q, then negation of R. It reads in words, if A is greater than B, if P, then integral x dx is log of x plus c. That's Q, P implies Q, if P and Q. And this whole thing is a conditional statement for negation of R. So if this is true, then a frog can fly. Okay, so this mathematical statement that P implies Q implies negation of R reads this way. And suppose your A is 4 and B is 3. Show that this statement is true. Okay, show that the S statement is true. Okay, do the remaining two examples same way. Understand the notation and concept, and do the proof. Okay. Next thing you want to have knowledge on is calculus. Actually, you need to have knowledge on multivariate calculus, but let's start with the simple one, univariate calculus. So this is a function f. And without getting into the deep notion of continuity and so on and so forth, suppose your f is continuous, then the first order derivative df of dx is defined this way, right? So df dx is defined this way, and for any given x. So for a value x naught, df dx at x naught is defined this way. I'm going to use this notation, okay? I'm going to use this notation to denote this. So it doesn't mean you do fx0 first. You compute f of x0 first and then take the derivative of this function, because this is always 0, right? So for the course, what this means is you do derivative first and then plug x naught value in the derivative. So you are going to evaluate the first order derivative at x naught. Okay. I hope you know what an indefinite integral is. And the fundamental theorems of calculus, there are two fundamental theorems of calculus. It's the relation between first order derivative and integral. Okay. Multivariate calculus. When you do multivariate calculus, you are using this notation. It's called the partial derivative. So, for example, here you have k-variate function f. If k is 2, then your function may be this. Your function may be this. Instead of using x, y, z, because we are going to get shortage of notation soon, we use sometimes this notation. So instead of using f, x, y, z, we may use f, x1, y, sorry. We may use fx1, x2, x3. Since in this example we only have three variables, let's use x, y, z. Then you can think of three partial derivatives: partial x, partial f, partial x, partial f, x, y, z, partial y, partial f, x, y, z, partial z. Okay. So in this notation, this j can run from 1 to k, and as you can see here, there's this missing f here. When you do the partial derivative with respect to xj, you take all other variables constant, fixed, and change only xj slightly by amount h, and then bring this h toward 0. Okay, so in this case, if you do this partial derivative, you are going to first compute f x plus h y z and subtract f x y z, divide this whole thing by h, bring the h toward 0. That's gonna give you this partial derivative of x with respect to x, f with respect to x. Here, now let's use this one, x plus h squared plus y squared, that's fx plus h and y, minus x squared plus y squared, that's fxy, and divide this whole thing by h, bring h for 0. Okay, then h over this y squared cancel this y squared here, so you get x plus h squared minus x squared. X plus h squared is x squared plus 2h x plus h squared minus x squared, limit h goes to 0, x squared cancel out, and this h cancel out, this 1 or this 2h's cancel out, so you get 2x plus h, limit h goes to 0, therefore it's gonna be 2x. So partial x squared plus y squared over partial x is 2x. Okay, what about this? If you're familiar with chain rule, you can see that it's going to be x plus y over 1. Okay. So use your undergraduate calculus books to do exercises for multivariate calculus. This one is pretty important. So this one tells you that, let's just use bivariate function. Okay, integral from, let's say, a to w f of x y dx, and you are going to do partial derivative with respect to w. Then it's f of w y. It's called the Leibniz rule. Okay, mean value theorem. Mean value theorem tells you that here, suppose this is your A, this is your Z. Then bring Z minus A in here, Z minus A. Then the left hand side is Z minus A, Fz minus Fa over Z minus A. So this is the slope of this line. And the mean value theorem tells you that under some conditions, of course, there is a point C such that the tangent line at the point equals has the same slope as this line segment here. Okay, it's called the mean value theorem. So mean value theorem is the existence of such points. Okay, Taylor approximation. So any function, for any function, any continuous function f, the idea of Taylor expansion is this. So this is your real line, this is your function, this is your function, and you don't know what this function is. And suppose this is your w, this is your w, and this is your z. Then okay. Then this part, this line, okay, this is not W, sorry, let me back up. Let's change the graph. Here's your real number, and here's your Z, and here's your F. Then this function is approximated depending on your W, of course. This function is approximated by this polynomial. Okay. For example, you can think of a linear approximation here. Okay. Then at least in this vicinity here, this linear function is a pretty good approximation of the true function f of w, right? And this linear approximation turned out is f of z plus dfz dx w minus z. That's gonna be your g of w. Okay. This this g of w is not f of w, but if in at least in this vicinity, is a good approximation. Okay. You can think of a quadratic function like this. Okay. Then in this vicinity, this quadratic function is a good approximation. And up to this part is the function. You can think of a cubic function here like this. Now change the color like this. Then it's a good approximation for this region. So for this region of W the f function can be written approximately by this cubic polynomial. Okay. If your f function is infinitely differentiable, then you can have infinite terms here, and the approximation can get closer to f function as your terms increase. Okay. All right. Numerical method. Suppose you are solving an equation. So you are going to get a solution of an equation. For example, suppose your equation is this. F of x is x minus e to the power x. Maybe plus 2. Okay. And you want to find the zero for this. So you want to find x star such that f star, which is x star minus e to the power x star plus e 2 equals to 0. So how would you solve this? Now the idea here is this. Suppose this function f of x looks like this. It may not look like this, but let's suppose this is your f of x. This is your f of x. And then this is going to be your x star. And the numerical method proposed here is is called the Newton's method. Is this algorithm? You start from any value here. Start from I think this would be nicer. So you start from here. That's gonna be your x, let's say naught, initial value. And then you take a linear equation. Oops. You take a linear equation here like this that goes tangent at this point. So this linear equation, the equation of this line is g. Let's say this is your g of x. G of x is f of x naught plus f prime of x naught times x minus x naught. How do I know that this is the line? First of all, at x naught, the value g of x naught is f of x naught. So what we know is g of x naught is f of x naught. And what we know, another thing we know is your g of x naught prime here is f of x naught prime, right? Because the line is a tangent line at x naught. So let's see if this function satisfies these two conditions. When you plug x naught here, then this part goes away. So your g of x naught is f of x naught. So this is checked. G of x prime, g prime is your g prime of x is by construction f prime x naught. Therefore, this is checked, right? So this line, this equation here is the equation of the line, and you set the second x, let's say x1 here, the solution of the line, the zero of the line. So this is your x1, the next step x1. So x1 satisfies this condition that f of x naught plus f prime of x naught, x1 minus x naught is 0. Okay. Therefore, your x1 is minus f of x naught over f prime of x naught. That's your plus. Sorry. Your x1 is x naught minus, that's your x1. So that's going to be your second x1. And plug this x1 to f of x and see if f of x1 is 0. In this example, the plugging of x1 gives you this value. This is your f of x1, which is not 0. So you repeat this process. Find out a line that gives the tangent to this point. Okay, and solve the line and call this point x2. So your x2 therefore is x1. You can see that x1 over f of x1 prime. And as you can see, the second x, the next one, x2, which we call x2, is closer to x star. So using this algorithm, you can get your new x closer to the previous from the previous x to your value x star. So you can summarize this algorithm by x of s plus 1, the s plus first x equals to the x minus f of xs over f prime of xs. And when do you stop? You stop f of xs is very close to 0, right? So your stopping rule, this is your algorithm, and stopping rule is your x star is x of s such that f of xs is actually 0, but in the numerical computation it's pretty hard to find correct exact 0. So what we do is you stop this algorithm, stop the algorithm when f of xs is very small. Okay. When your f value at xs is very close to 0, and then you claim that your numerical solution is xs. Okay, that's how you solve numerically an equation. Now let's use this idea to the minimization problem. Suppose you are doing this minimization, min q of theta. Theta is a scalar. Okay, we are going to do the vector version later, and q may be very complicated. So when you minimize this one, suppose this is your q. What you can see here is at the minimum, your q prime theta is 0, right? So instead of q, let's focus on q prime. So q prime, here's your q space. Your q prime, if you think about q prime, in this region, your q prime is negative. In this region, your q prime is positive. So it goes this way. Okay. May not be line. So let's just use a function that is not a line. Okay, so let's say this. And you want to find the solution. This is your q prime of theta. So what you can see here is you can use the algorithm qs plus 1 equals to q of s, sorry, not q, theta I meant. Theta s plus 1 equals to theta s minus q prime of theta s over q double prime theta s until q prime of theta s is very small, right? This algorithm is called Gauss-Newton method. Okay. Now let's take some break and I'm gonna continue with linear algebra.